we will talk about the graphical representation and understanding of the equation of kinematics. And we already have talked about the three equations of kinematics. For the sake of this lecture, I will assume xi to be 0 and ti to be 0, which means the initial position is 0 and initial time is 0. With this we can write Vf equals Vi plus At, let's call Tf T because we do not have Ti anymore. Also we know that Vf square equals Vi square plus 2 Ax, let's call Xf as x, and also we know that x equals Vit plus half At squared, right? And there are well, so let's see, let's talk about several cases here. Let's take a case when a is 0. When a is 0, then so let's number them first. This is the first one, this is the second one, this is the third one. The third one looks like x equals Vit, which means this is a motion with constant velocity. And if you graph, again you choose your, well, this is not axis system, this is something else. This is called displacement time graph. So if you plot x, the displacement on the x-axis, on the y-axis, and time on the x-axis, you see that this is actually equation of a line. So this is x equals Vit. So on a displacement time graph, constant velocity is a sloped line. This is already very useful once we go through this. Let's take one more example. If we still have a constant velocity, but instead of a displacement time graph, let's say we have a velocity time graph. Now how would you draw constant velocity on this graph? Let's use one of the equations. Now if you look at this particular equation, we see if a is 0, Vi is same as Vf, which means V was constant all the time. So this is how a constant velocity should look like on a velocity time graph, right? Let's take one more example. Now let's assume we have acceleration, and if we have acceleration, which means velocity is changing with time, so how would you make that graph? And let's draw a case of constant A, this is constant V, this is constant A. For constant A on a velocity time graph, okay, how would you draw this? Well, let's use one of these equations. Well, not one of them, this should be the first one, because this is the equation that is relating velocity with acceleration. So if acceleration is constant and there is some initial velocity, you see this is nothing but equation of a line, and then this is how it should look like, and this is Vi, and we know the slope is going to be what? It's going to be a, because slope is a here. Similarly, slope will be velocity, or v, for this graph, because that's how the equation of line is. For equation of line, you see, you're plotting this on the x-axis and this on the y-axis, so term which multiplies the x term is the slope, so this is slope. Similarly here, you're plotting this on the y-axis, this on the x-axis, and this is slope, so that goes here. Okay, let's see how the same thing, which means the constant acceleration graph, will look like on a displacement time graph, right? So x is plotted on the y-axis. Now these are just graphs. We are not really trying to define a frame of reference or set of axes to solve a problem. This is just simple mathematical graphs. So please don't get confused with the axis system we were defining in the last few examples. Alright, so with this graph, you see it's this equation that is going to be plotted, and this should look like something like that, and we know this actually is parabola. This is a parabola. Okay, so these are the various ways in which you plot things. Alright, let's try to understand a few more things. And now if you have, let's say, a velocity time graph, and let's say velocity change like this. Now there's a meaning to the statement that the area covered under the velocity time graph is displacement. So this whole area is displacement, which is xf minus xi. How to understand this? Well, if you take a slice here, for this particular slice, let's assume v is a constant. If v is a constant, that means the height is constant. Well, it's not really constant, but because we have taken a very thin slice, we assume v is constant throughout this rectangle, and there's a small delta t. So we're not talking about instantaneous velocity. The small delta t is the time for which we assume v to be constant, and for this case, you can see we can assume this to be a small rectangle, right? So if we, let's say if this velocity is v, I don't know, v naught, so in the area of this, the area of the rectangle is going to be v naught t, the small area. Consider one of these equations, first one, in which we have a constant v naught delta t is here. V naught delta t is actually delta x. This is nothing but change in displacement. And if you sum up all these displacements, which means here, 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 which covers the whole area, then we actually sum up all the small displacements, and this should be xf minus xi. And the same holds true if you have an acceleration time graph then Using the same logic, you will find out that area under curve is VF minus VI. So let's recapitulate. Slope of xt graph is velocity. Slope of vt graph is acceleration. Area under curve for vt graph is displacement, and area under curve for at graph is change in velocity, right? So this I did not really do a very good job of explaining this, but if you give it a thought, you will understand. The first two is because of the nature of this equation of line, and the second two is because we are summing up all the areas and trying to find out the change in displacement.